The largest machines ever built cannot be delivered. They are too tall for any bridge, too wide for any road, and too heavy for any transport that exists on Earth. So they are not manufactured in a factory and shipped to a customer. They arrive at a mine as thousands of separate pieces over months, and they are assembled in an open pit, in the weather, by crews who spend years putting a single machine together. And when the coal runs out, most of them are cut apart in the exact spot where they were born. Today we are looking at how the biggest mining machines in the world actually come into existence, what it takes to deliver them, how they are assembled, how they move when nothing on the planet can carry them, and what happens to them at the end. In 1969, a coal mine in southeastern Ohio took delivery of a machine. It came on more than 300 rail cars and 250 trucks. Then a crane was built. Not brought in, built. A stiff-leg derrick, erected on site for one purpose, which was to assemble the pile of parts that had just arrived. What they put together was called Big Muskie, 73 meters tall, 13,000 tons, a boom stretching 100 meters, and a bucket that could hold 325 tons of earth in a single scoop, large enough to park 2 inner-city buses inside it, side by side. It was a Bucyrus Erie Model 4250-W, and only one was ever built. There is a reason for that. Nothing about it was standard, and nothing about it could be reused anywhere else. The components tell you how far outside normal engineering this was. The chain links on the bucket rigging were forged rather than cast, because a cast link of that size would hide voids inside the metal that could fail under load. Each link weighed around 1,000 pounds. The wire rope running through the system was roughly 5 inches thick, which is heavier than the mooring cable on most ships. And every single one of those pieces had to be small enough to fit on a rail car or a truck bed, because there was no other way to get them to rural Ohio. That is the constraint that shapes everything about these machines. They are designed backward from transport limits. Every component is sized not by what would be strongest or simplest, but by what can physically travel on existing infrastructure and then be joined together on site by welders standing in a pit. Assembly took over a year. Crews worked outdoors through Ohio winters, bolting and welding sections that had been fabricated hundreds of miles away and had to fit together within millimeters. When it finally started digging, Big Muskie was operated by a crew that sat in a control house perched on the rotating body of the machine, high above the working face. From up there, the operator swung a boom the length of a football field and dropped a bucket the size of a house onto ground he could see but could not really judge, over and over, for a full shift. Over 22 years of work, Big Muskie moved approximately twice the volume of earth that was excavated to build the Panama Canal. One machine, one mine. It never went anywhere else. Here is how absurd the transport problem gets at this scale. In 2001, a dragline called Ursa Major went into service at the Black Thunder mine in Wyoming. It is smaller than Big Muskie was, and it is currently the largest walking dragline still working anywhere in the world. Its bucket alone weighs 82 tons. Just to move that bucket to the mine, Bucyrus had to obtain special permits for an oversized and overweight load. Then they had to contact the electric utility along the route to confirm the bucket would not strike any power lines on the way. That is one component, not the boom, not the house, not the machinery deck. A single bucket requiring government permits and a power line survey to travel by road. Now multiply that by every piece of a machine weighing 6,700 tons, which is nothing compared to what the Germans did. In 1978, a bucket wheel excavator entered service in Western Germany that is still among the largest land machines on Earth nearly 50 years later. Bagger 288, 225 meters long, 96 meters tall, 13,500 tons. 96 meters is roughly the height of the Statue of Liberty, measured from the base of the pedestal to the tip of the torch. That is not a comparison to a building, that is a comparison to a monument. But the number that matters here is the timeline. 5 years to design and manufacture the components, then another 5 years to assemble them. 10 years from decision to first dig, roughly $100 million in 1970s money. The reason it took that long is that almost nothing on the machine could be ordered from a supplier. When Krupp began the design, no engineering precedent existed at this scale. The bearings had to be developed from scratch because nothing on the market could carry those loads at that diameter. New fabrication methods had to be invented because the steel sections were larger than anything the company had ever produced. And the assembly sequence itself had to be created from nothing because no one had ever built a machine like this and there was no procedure to follow. Think about what that means in practice. Before the first piece of steel was cut, engineers had to answer a question nobody had ever answered. In what order do you assemble something this large, on open ground, using cranes that are themselves near their limits, without any part of the half-finished structure collapsing under its own weight? The answer to that question was 5 years of work on its own. The parts were fabricated in modules, shipped separately to the mine, and then crews spent another 5 years in the pit turning them into a machine. What they assembled works nothing like a dragline. At the end of a long boom sits a wheel 21 meters across, carrying 18 buckets around its rim. The wheel turns continuously. Each bucket bites into the working face, lifts as it rotates upward, and empties onto a conveyor belt running back through the machine. There is no cycle, no swing, dump, and return. The wheel simply rotates and the earth flows onto the belts in a continuous stream, hour after hour, all day. The output is 240,000 cubic meters of material per day, more than 10,000 dump truck loads every day from one machine. Operated by a crew of 5. It has no engine. Bagger 288 is fed 30,000 volts through cables trailing behind it, roughly 16 megawatts of electricity, and it contains more than 120 kilometers of internal wiring. If you laid that cabling end to end, it would stretch from one city to the next. And despite weighing 13,500 tons, it barely marks the ground. The weight is distributed across 12 crawler tracks, 8 at the front and 4 at the rear, spread over such a large area that in soft soil the machine leaves tracks no deeper than a human footprint. 13,500 tons, walking over grass without sinking in. 17 years later, the same country built something heavier. Bagger 293 came out of the Tokraf works in 1995. Same length, same height, but 14,200 tons and buckets holding 15 cubic meters each instead of 6.6. It holds the Guinness record as the heaviest land vehicle ever built, and it still holds it today, 3 decades later. The reason the successor exists at all is worth understanding. These machines are not built to be impressive. They are built because at a certain scale of open-pit mining, continuous excavation becomes dramatically cheaper per ton than any alternative. A bucket wheel excavator replaces an entire fleet of trucks and shovels, along with the fuel, drivers, maintenance, and haul roads that fleet would require. Bagger 293 needs about 1.2 kilowatt hours of electricity to move a cubic meter of earth. That is roughly what a household refrigerator uses in a day to move a volume of soil the size of a small car. The machines are enormous because enormous, in this specific application, is efficient. So what happens when the mine one of them was built for runs out? In 2001, Bagger 288 finished at the Hambach mine and was needed at Garzweiler, 22 kilometers away. 22 kilometers is a short drive. For this machine, it was an expedition. Bagger 288 moves under its own power at between 2 and 10 meters per minute. At full speed, that is 600 meters in an hour. A person walking normally covers that distance in 7 minutes. The journey took about 3 weeks. And the driving was the easy part. The machine is 46 meters wide, so nothing along the route could be narrower than that. Roads had to be reinforced or written off entirely. A river crossing had to be arranged. Rail lines had to be dealt with. And every overhead power line along the path had to be raised or temporarily removed because the top of the machine sits 96 meters in the air and cables do not move on their own. The electricity supply had to follow it. The machine runs on cable-fed power, so the entire high-voltage feed was extended and rerouted continuously as it advanced. There is also the question of what the ground does underneath. 13,500 tons crossing farmland, forest tracks, and buried utilities means the route has to be surveyed for anything that might collapse. Old mine workings, drainage culverts, gas lines, water mains. Every one of them either reinforced, rerouted, or avoided. Roughly 70 people were involved. The move cost millions. And it was still far cheaper than dismantling the machine, hauling it in pieces, and rebuilding it, which would have taken years and risked destroying components that no longer had suppliers. If you appreciate engineering told this way, take 1 second to subscribe and drop a comment telling us where you are watching from. It helps these videos reach people who care about how things get made. Draglines solve the movement problem in a completely different way, and watching it happen is genuinely strange. A walking dragline has no tracks and no wheels. It sits on a large circular base called a tub, which rests flat on the ground and carries the entire weight of the machine while it digs. To move, it uses 2 enormous shoes, one on each side, mounted on rotating eccentric cams. The shoes lower to the ground. The cams turn, which lifts the tub slightly off the earth and shifts the whole machine backward by a few meters. Then the shoes lift, the tub settles down, and the cycle repeats. It does not roll, and it does not drive. It lifts itself, shuffles backward, and sets itself down again, over and over, a few meters per minute. There is a reason draglines walk backward rather than forward. The machine digs in front of itself and dumps the material behind, which means the working face is always ahead and the spoil pile is always behind. As the pit advances, the dragline retreats from the edge it is cutting, staying on solid ground and never driving out onto material it just dumped. Thousands of tons of steel, walking away from the hole it just dug. There is a part of this story that almost never gets told, which is what the assembly itself is actually like for the people doing it. A mine that has ordered a machine of this class is committing to years of construction before it produces anything. During that time, the pit runs a second operation alongside the mining, with its own workforce, its own cranes, its own scheduling, and its own hazards. Welders work at height on structures that are not yet stable, in weather that does not stop for them, joining sections that were fabricated in a controlled factory and must now fit together outdoors within tolerances measured in millimeters. Steel that has been shipped across a continent arrives warped by handling and temperature and has to be pulled back into alignment by jacks and heat before it can be joined. And unlike a building, there is no scaffold system designed for the job because the job has never been done before. Crews spend so long on a single machine that people take work on these projects the way others take work on a ship. They arrive, they live nearby, and they stay until the thing they came to build is finished. Some of the workers who assembled these machines watch them run for the rest of their careers. But no mining.
A machine has ever walked further from what it was built to be than this next one. In the Lusatian coalfields of eastern Germany, there is a machine that holds a record most people have never heard of. It is called the F60, and it is the largest vehicle by physical dimensions ever built by human beings. 502 meters long, 240 meters wide, 80 meters tall, 13,600 tons in operating condition. It is longer than the Eiffel Tower is tall, by a wide margin, which is why Germans call it the Lying Eiffel Tower. What it does is remove overburden, the layer of soil and rock sitting on top of a coal seam. 2 bucket chain excavators mounted on the structure strip the material and feed it onto conveyor belts, which carry it the full length of the bridge and dump it on the far side of the mine. That is the entire concept. Instead of loading soil into trucks and driving it around the pit, you build a bridge across the pit and let a conveyor belt do the work. The material never touches a wheel. The name comes from its capability. F60 means it can cut through 60 meters of overburden. The 2 excavators together move up to 50,000 tons of material per hour. The whole thing rides on 760 wheels running on rails, 380 of them powered, at an operating speed of about half a kilometer per hour. The crew that runs it numbers 14 people. 14 people operating the largest vehicle ever constructed. 5 of these were built by the East German state combine Tachraf between 1969 and 1991. 4 are still working today in the Lusatian mines. The 5th one has a different story. Construction on the last F60 began in Lichterfeld in 1988, while the region was still East Germany. It took 3 years to build. It entered service in March 1991. In June 1992, it was shut down. 13 months. That is the entire working life of the largest vehicle ever constructed. German reunification had changed the country's energy policy. Lignite from that region was no longer economically viable under the new market conditions, and the open pit it was built to serve was closed. The machine had been under construction more than twice as long as it had operated. The plan was to scrap it. The mining company that inherited it intended to dismantle the structure and sell the steel, which is what happens to almost every machine at this scale when its mine dies. There were even proposals to bring it down with controlled explosives. Local residents fought to keep it. Their argument was that the region was losing its industry, its jobs, and its identity all at once, and that the F-60 was the last physical evidence that any of it had happened. If it went to the scrapyard, there would be nothing left to show what had been built there. They won. In May 2002, the F-60 opened to the public as a visitor attraction. Guided tours walk groups along the structure, 90 minutes at a time, climbing onto a machine that most of them had watched being built. By 2016, it was drawing around 75,000 visitors a year. A machine that worked for 13 months has now been a tourist site for over 20 years. Everything so far has been about machines that essentially never leave. The modern industry went a different direction. In Zhojina, Belarus, there is a factory that builds the largest dump truck in the world. The BelAZ 75710 carries 450 metric tons of payload. Empty, it weighs 360 tons. Fully loaded, 810. 2 diesel engines, 2,300 horsepower each, 4,600 combined. Those engines do not drive the wheels. They generate electricity, which powers electric motors at the wheels. The same principle as a diesel-electric locomotive, because no mechanical transmission would survive that torque. Top speed is 64 kilometers per hour, though in a pit it typically runs between 20 and 40. And like everything else at this scale, it does not arrive assembled. It ships in components and is put together at the mine. But the assembly is not the end of the obligation. It is the beginning. You cannot service a truck this size in a conventional workshop. Mining companies have to construct dedicated facilities with ceilings high enough to clear a raised dump body, overhead cranes rated for components weighing tens of tons, and floors reinforced to carry the vehicle without cracking. Changing a single engine is not a job for 2 mechanics and a hoist. It requires a crane, a crew, a purpose-built bay, and days of scheduled downtime that has to be planned around production targets. The truck does not just arrive at the mine. It requires the mine to build a building for it. And then there are the tires. The BelAZ rides on 8 of them. Each one stands 4 meters tall and weighs more than 5 tons. Those tires are one of the genuine bottlenecks in global mining. Only a small number of manufacturers in the world can produce tires at that size. Each one takes a long time to build because the rubber has to be laid up in layers and cured for hours in a press the size of a room. And the internal steel belt structure has to be built to survive a load of over 100 tons per wheel on broken rock. Each one costs tens of thousands of dollars. There have been periods where mining companies planned their operations around tire availability rather than truck availability, because a haul truck without tires is an extremely expensive sculpture. It also means the haul roads themselves become critical infrastructure. A road that develops potholes will destroy tires that cost more than a house, so entire fleets of graders and water trucks exist for no purpose other than keeping the surface smooth enough that the tires survive. The water trucks matter more than people expect. A dry haul road generates dust that destroys visibility and gets into every filter and bearing on every machine in the pit. So a separate fleet of trucks does nothing but spray water on roads continuously all day so that other trucks can drive on them. The truck is also useless without the machine that fills it. A haul truck this size is not loaded by a normal excavator. It is loaded by an ultra-class electric rope shovel, a machine roughly 14 meters tall, carrying a bucket that holds 40 to 60 cubic meters. Those shovels have the same delivery problem as everything else. They arrive at the mine in pieces and are assembled on site over weeks, using mobile cranes that themselves have to be trucked in and built up first. The crawler tracks alone can weigh dozens of tons per section. And like the bucket wheel excavators, most of them run on external electrical power rather than diesel, fed by a heavy trailing cable that has to be managed constantly so the machine does not drive over its own power supply. 3 passes of that shovel fill the truck. Each pass takes 30 to 40 seconds. The complete cycle, including positioning the truck, runs about 3 to 4 minutes. Then that truck pulls away, the next one moves into position, and the shovel starts again. All day, all night. None of these machines work alone. The shovel is worthless without trucks. The trucks are worthless without the shovel. Both are worthless without the road crew, the water trucks, the fuel bays, the tire shop, and the electrical crews who move and repair the trailing cables. Every one of these enormous machines is a single component inside a system that only functions if the entire thing runs. If you are finding this interesting, hit like. These take an enormous amount of research to put together, and it is what tells the algorithm to show them to people who want to learn. Which brings us back to Ohio, because a machine that was assembled in a pit and can only be moved by walking has one final problem. What do you do with it when it is finished? Big Muskie stopped working in 1991. It was not worn out, and it was not broken. The machine was still fully capable of doing what it had been built to do. What changed was the law. The Clean Air Act amendments of 1990 sharply restricted sulfur dioxide emissions from power plants. The coal that Big Muskie had spent 2 decades uncovering was high sulfur coal, and demand for it collapsed almost immediately. At the same time, operating costs kept climbing. Electricity, maintenance, crew, and replacement parts for a one-of-a-kind machine with no production line behind it and no other customer to share the tooling cost. Eventually, the cost of running Big Muskie exceeded the value of the coal it was exposing. So they parked it. And once parked, there was no second life available. It could not be sold because no other mine could physically receive it. It could not be relocated because the only way to move a dragline is to walk it, and walking it across Ohio was not remotely economical. It could not be converted to anything else because it had exactly one function. It sat idle for 8 years, outdoors, on the same ground where it had been assembled 30 years earlier. In 1999, it was cut apart for scrap. Crews with torches worked through a machine that had taken over a year to assemble. The steel that had arrived on 300 rail cars left on trucks sold by weight. One piece was saved. The bucket sits today in a park in southeastern Ohio on public display. Visitors walk inside it. People stand underneath the opening for photographs, and the scale only registers when someone stands next to the chain links, each one weighing about as much as a small car. It is the only surviving piece of the largest walking dragline ever built. Everything else went to a steel mill. And that is the normal ending. These machines are conceived for one specific deposit, assembled at that deposit over years, and when the deposit is exhausted or the market shifts, they have nowhere to go. A few get walked to a neighboring pit if one happens to exist close enough. Most are cut up where they stand. The same thing happened to the machine that Bagger 288 dethroned. Before 1978, the heaviest land vehicle in the world was an American stripping shovel called the Captain, working in Illinois. It weighed roughly 12,700 tons. It caught fire in 1991 and was scrapped shortly afterward. Nothing of it survives. Bagger 288 was lucky. When Hambach was finished with it, Garzweiler needed it, and Garzweiler was 22 kilometers away, which was just barely close enough to justify a 3-week walk across the German countryside. Had that second mine not existed, one of the largest machines ever built would have been scrapped in the pit where it was born. The F-60 was luckier still, and only because a group of local residents refused to let it be demolished. 300 rail cars for one machine. A crane built specifically to build another machine. 10 years of design and assembly for a third, including 5 years just to work out the order in which the pieces could safely be joined. A single bucket that needed government permits and a power line survey just to travel by road. A 22-kilometer move that took 3 weeks, 70 people, and the rerouting of roads, rivers, railways, and the electrical grid. None of these were manufactured and delivered the way every other machine on Earth is manufactured and delivered. They are assembled in the pit from parts that arrive over months. They work in the place they were built. And when the reason for their existence disappears, most of them are dismantled on the same ground. There is a bucket sitting in an Ohio park right now, big enough to walk into, that is all that remains of a machine which moved twice as much earth as the Panama Canal excavation. And in Germany, 75,000 people a year buy a ticket to walk along a machine that only worked for 13 months. Every megastructure we take apart on this channel starts with a question from someone watching. What should we decode next? Put it in the comments. Hit subscribe and turn on notifications. The next one goes even bigger.